Hello everyone, welcome to the P1 program. This lecture is called P105.3. In this lecture, I'm going to introduce the concept of area under a curve and the integration, and I'm going to do one simple problem. Okay, so before that, I'll recap what we have done. We have done the mean value theorem, which says that if you travel, as for an example, if you travel into distance say 3000 kilometers in 100 with an average speed of say 100 uh, kilometer per hour, 3000 kilometers. So if you travel in with an average speed of 100 kilometer per hour, then your odometer, your total time taken for that travel will be around 30 hours, right? So 30 hours would be taken for you to reach from point A to point B. So in that traveling, you will actually your speedometer will detect a speed of 100 meters at some point. Okay, that's the mean value theorem. The mean value of speed, right? If you travel with the speed of 100 say 50 kilometer per hour, which is a lower speed, and you travel at 150 kilometer per hour, which is a higher speed, then the average speed is 100 kilometers per hour. So in that range of speed, you will at least once hit the speed 100 kilometer per hour. That's the mean value theorem significance. So you cannot skip that part. Okay, that's the mean value theorem significance. And also what you can do is that when you have a plot of um, say what displacement versus time graph or anything like that, or displacement versus time graph, and it looks like that, and you draw a velocity versus time graph using that part, and you can actually what you can actually do is that you can draw another parallel line, any line like that, a parallel line to the velocity time graph, and you can move around this line, and you hit a point where the slope of that line is actually equal to the slope of this graph. So slope of this velocity versus displacement versus time graphs. So displacement versus time graphs slope will meet with the velocity versus time graphs um, slope. So that point is actually called, in this case it will be around here, right? So in this point, this graph will have the actual tangent, which is equal to the velocity versus time graph. So that means that it has the same slope. That means that's the mean value. Okay, that's a easy way of identifying the mean value. So that's mean value theorem, and that's what we did last time. And now what we are going to do is that we are going to start with a basic simple problem. So for that, I'm going to consider a case of a car. So this is a car. Okay, this is some kind of a car. Okay, there is the car, and you are at a parking spot. You are at a signal, a traffic signal. So there is a yellow light here, there is red light here, and there is green light. Okay, it could be reversed anyway, and you are currently at a red light. Okay, and then you have to turn to green, and then only you can move. Okay, so you are at rest now. Your motion is at rest now, and you are waiting for the light to turn the signal. Now there is one another thing, which is a bus. Okay, there is a bus now, looks like that, a simple bus, and it is coming from this direction with with a velocity of 16 meter per second, and the car is at rest, and it has an acceleration, it has an acceleration of 3 meter per second. Okay, that's the acceleration, second square. That's the acceleration that the bus can have. That's the acceleration that the car can have, and this is the velocity of the bus. Now when the suddenly at this point, this when bus reaches the initial starting point, suddenly the signal turns to green, and both of them start from 0 to that point. This is x0. Both of them start at the same time. One has no acceleration, the bus has no acceleration. So acceleration of bus is equal to 0. Well, the velocity of bus is 16 meter per second, and the acceleration of car, which is equal to 3 meter per second square, and the initial velocity of car is 0. So that's the situation right here. Now what we need to find out is the actual, what is the, if you plot this both thing, right, displacement versus time graph, you'll see that the car will be accelerating, so it will be a steeper curve, and the displacement curve will be a steeper one. But the what the bus is not accelerating. That means that the plot will be a straight line. So at some point these two lines will meet. Okay, then in that point, what happens in that point is that the car is going to overtake. So in that point the car is going to overtake the bus, right? So that's the significance of that point. You can imagine the initial stage of this car. The car was sitting at rest and the bus was moving from this direction, and when it reached here the signal turned and both of them started moving in this direction. So they were initially at rest and they started moving, and at some point the car is going to overtake the bus, right? We need to find that point, and what's the time is going to take. A time will be taken for that overtaking. So what we can do is that we can write down the equations of motion, which is say x, sorry about that, x equal to x0 plus v0 t plus half at square, which is the equation of motion. So for the car you can write down that x0 is 0. For car x0 is 0, the initial starting point is 0, the velocity of the car at rest is 0, and the acceleration of the car is 3 meter per second. So that's 3 by 2 t square, right? And also the case of a bus, it will, the initial starting point is 0 for the same, and the velocity was what, 16 meter per second. So it's 16 times t plus acceleration is 0. So it is having a constant velocity, no acceleration, so it's 0. So you can see that when xp equal to xc, right, in the graph you can see when xc equal to xb, that distance is when the car is going to overtake the bus. So you can equate that when x equal to xb, it will become 3 by 2 t square, to t square will be equal to 16t, right? So you can easily write down that t will be equal to 16 times 2 by 3. So that will be approximately, it's 32 by what, 3. So it will be around 10.6 seconds. You can approximate to 11 seconds. Okay, I'm doing an approximate method here. Okay, that's the time taken for this car to overtake, right? So in that time, what will happen, what will be the distance traveled in that by the car and the bus in order for the car to overtake the bus. So you can just straightforward put back this into the equation of car or bus, so that you can directly find out the velocity. So the displacement, so you can write down the xc or xb, which is the same. So I'm taking what, xc here, or xb, which is 16 times t. So that's 16 times uh, times 11, which is around 170 or 75 meters or something like. So you can actually calculate it yourself. Anyways, this is the approximate distance it is going to travel, right? So it's the approximate distance it's going to travel, and that's the time taken. So this is a very straightforward 8th standard problem that we have done. So it's an easy way of representing one-dimensional motion. Now what I'm going to introduce now, I'm doing more problems because some of you guys requested me that you need more problems in the lectures. So that's why one-dimensional simple problems are being done here. So anyways, let's get into the integration. Okay, area under the curve. So we already know that, we already have substantially mentioned that an area under the curve for the displacement versus time graph, the area under this curve is the distance, right? So that's the distance. And for the say the velocity versus time graph, the area under the curve will be the displacement, the total displacement. And for the acceleration versus time graph, the area under the curve will be the total velocity. So that's a thing I have uh, made clear in the last lectures. Now what I'm going to do is that I'm going to look at this in a different perspective. So different perspective is where we look at. Okay, so if you take a velocity versus time graph like that, what you can initially see is that for the whole change in with respect to v, which you can call delta v, with the change in t, which you can call delta t. Okay, when it gets to some limiting value of delta t tends to 0, it can be called as dv by dt, right? You can call it. Okay, we did that earlier. Now what what is this dv? Okay, this dv and dt are called Leibniz differentials. So these are notations for differential. So dv by dt, when you time derivative, when you take the time ratio of change in velocity, it's called the acceleration. So this is the acceleration anyways, right? So you can clearly understand that this is the acceleration. Now what we can do is that the Leibniz differential dv means that there is a change. It denotes a change in the axis, v axis. So it's a some small change in the v-axis, and dt denotes the small change in the time axis. So that's Leibniz differentials dv and dt stands for. Now what you can do is that if you have a small part of the v, which is dv, and a small part of the t axis, which is dt, and if you can rearrange this equation, and you can say dv is equal to a times dt, right? A times dt, sorry about that. So if that's a times dt, then now what you can do is that you can sum all these small parts, right? You can do a summation of all these small parts into a big one, right? And also the v-axis as well. So v-axis and t-axis can be summed over, right? So what you can now do is that you can write it like sigma I equal to, say, 0 to what, some n vi must be equal to some a times sigma I equal to uh, 0 to n some ti. You can write it down like a summation, and this summation is actually the differential. So this summation is called some differential of 0 to say y dy, or okay, sorry about that, it's not dy, it's integral 0 to b dv, which is equal to a times integral 0 to t dt. So this summation is actually called the integration. Okay, this summation is actually, the integration stands for that summation. Okay, so what we have done here is that we have took the whole part, right? The variations in the whole part, and represented it in a terms of an equation of acceleration. So that's what we have done here. Okay, so what is the benefit of doing this addition or integration? So when you, what you can benefit from this is that there is a generalization. There is a generalization of v and t differences. The variations are accounted for, and there is a generalization. Now what's the objective here is, when you integrate this, you get v plus some c1, right? V plus some c1 must be equal to a times t plus some c2, right? So when you take the graph like this, right, this graph for v versus a time graph, and you see that at t is equal to 0, at t equal to 0, v is equal to 0, right? So you can substitute that back into this equation, and you get v is t is equal to 0, you get v equal to 0. So c1 is equal to c2, right? C1 is equal to c2. That's the basic thing that you get, and you can cancel that c1 and c2 from the either sides. and you get, because they are both the equal, you get v is equal to 80. So there's a fundamental equation that you get back from that kind of a equation generalization, where v is equal to 0 at t equal to 0. If there is a there is a change in this plot, there is some kind of a difference in this plot, like starting from here, you can see clearly see that this c1, right, new constant, will add back into this equation, right? So at t equal to 0, what you will find that t is equal to 0, v is equal to some c1 at t is equal to 0, right? You can substitute back that equation, and you find that v is equal to uh, some c1 or c, say c2 or c3, let it be c3. So v is equal to c3. So in this equation you can substitute that back, and you get c3 plus c2, c1 is equal to f t1, which is equal to 0, plus c2, right? So c3 is just c2 plus c1, right? So what you can now do is that you can introduce that c3 into this equation, and it will form a new equation with a new constant. So that's how you that's how integration works and manages the changes in fluctuations of this equation. So that's a very basic idea and crude idea. So we are going to do something which is more clear cut and clarifying for you guys to understand what is actually happening with the integration. So let me take this let this be your plot. Okay, this is the plot of velocity versus time graph, right? And in this plot, I need to find out is the area under the curve. Now if the area under the curve is, if you want to integrate or differentiate, if you want to integrate, then you can fix a point. Okay, let this be one point and this be the other point, and you can draw a perfect surface around it, and you can find out, you need to find out this area within this region, right? That's what you need to find out. Now what you can do is that if you take a midpoint, if you take a midpoint here, and you now draw this area. Okay, let this be the whole thing, right? Now if you look at this area and this area, right? So we, what we need is this area, we don't need this area, right? So we, what we need to do is that add the area of this whole thing with with along with this area, and then subtract the this area, right? That's what we need to do. I'm going to redraw it in a simple manner, right? So you can draw it like this is the curve, this is the curve, and the area is like that, right? So we took the midpoint, that means this distance must be the same, and this height must also be the same, because the slope of the curve is the same. Okay, we are going to take a small part in the whole curve where the slope is almost remaining the same, right? So if it's a curve like that, it won't work. But what we can do is that we can break it down to smaller parts and then magnify it, and so that the slope between these 2 points are the same. So if the slopes are the same, then that means the x distances and the y distance, let this be y distances, be the same. So this triangle or this shape is has almost the same area, right? So what you can do is that you can remove this part, you can remove this part and add this part, and so that it will become something like this, right? So the shape has become something like this, where this is the t-axis and this is the velocity axis. So now the whole area under the curve, which is equal to vt, right? So vt means displacement. So area under the curve is called the displacement. So it's a very simple and crude way of understanding what's happening. Now all we need to do is that if you do the integral, we find that the area under the curve is going to be the displacement. Now if we can add all these small x elements and all small y elements, and then find the ratio, or you can say it like that, if you integrate v the all the small v elements and integrate all the small time elements and multiply it with a, you get they a very good equation, and it will satisfy, it must satisfy, because what you're doing is you are limiting to some area and you're adding all those values, all those variations in that place. Okay, so if you have a non-accelerate, if it is not an accelerated system, if it is not an accelerated system, or you can say if it is a, it's a varying acceleration, let a be what you can say, let a be, let a be, a is equal to some c times x square. Okay, let it be like that. Now if you what you can do is, you if you integrate this a with respect to t, okay, let this be in terms of t, right, so that you have a sense of notation. A t square, okay, let it be c a is c t square. So if you, what you do is, when you integrate, when you integrate a, right, dA with respect to some dt, what you get is for all spaces or for all the lengths, okay, for all the lengths and breadths, when you integrate for all the distances of t, when you integrate that, you will get uh, ct square, which is the integral of ct square dt, right? So that's the area under the curve, which is total velocity. So this is the velocity. So this will be some ct cube by 3 plus c1. Okay, that's a first constant here. Now this is an equation, okay, which is not familiar for you guys, but you can imagine that if a was equal to some constant, the integral will be v will be integral of a times dt, which will be ct. So it's some form of v is equal to x0 plus vt, right? So it's in some form. So that's what we are going to get. So this is actually the velocity equation, which is a power of t cube, right, which is a power of t cube. So a was having some power of t square. Now v has some new power, which is more steep and more climbing than a. Okay, so it's much more steeper. Now the next thing you can do is that we can integrate this again, and you can integrate v with the whole, in the whole space of t time dimension, and you get c t raised to 4 by 12 plus c1x plus some constant c2, right? So that's what you get, and this represents the displacement, right? So this represents the displacement of this whole thing. So you can easily do that with the integration. You can find the area. This is the actual area under that curve of velocity time graph. So velocity time graph, the curve, the area under that curve is actually the displacement, and we found it straightforward using the Leibniz differential, and we just integrated that differential, that small element, into a whole bigger element, and it became a bigger element, and that value gave us the whole of area. So that's easy as that. This is a very simple concept, but it's a very deep and need much more understanding if you want to apply it somewhere. Okay, so that's the a velocity, that's a whole displacement here, and this velocity curve, the integral of the acceleration gave us the velocity, and the integral of acceleration gave us the velocity, and integral of velocity gives us the displacement. So that's what we can do, and that's a basic thing. And I'm going to do another example which is probably in the next video. Okay, thank you for watching. And if you have any feedback regarding the speed or anything like that, I'm going as slow as possible, because I want all the persons, right, all the people to understand this stuff. And there are people who are slower than you, and you could always skip through this material. If it's a video, then it's easy to move through this material. You can fast forward it, you can skip some content. But those people who are not fast enough, they cannot capture anything if I'm not saying anything, right? So that's why I'm going this deep, and thank you for watching. All the best, you guys.